Okay, so now that we've closed our integration path, we know what the answer should be. According to the residue theorem, the answer should just be 2 pi I, and then times by the sum of the residues inside C. But there's only one singular point inside our contour C, and that is the point plus I. So we should get 2 pi I times by the residue at I. So now we want to calculate the residue at I. So how do we do that? Well, so we want to take our function, which is 1 over x plus I, x minus I, and we'd like a Laurent expansion. So we want some sort of an expansion like this. N is equal to minus infinity to infinity. We want Cn, and then what we're going to have, x minus I to the n. And you can see that when we set x equal to I, all of the negative terms are going to produce singularities. Okay, so let's now try to get hold of this Laurent expansion. Well, we can write this function as 1 over x minus I plus 2I for the first bracket, and then x minus I. So I'm just getting hold of the x minus i's everywhere, and then I can write things as follows. 1 over 2I, 1 over x minus I, and then 1 over, let's write this as, we'll have a 1, we've taken x minus I, we divide it by 2I. Let me put in a minus here, so a minus sign there, and a minus there. And the reason why I want to write it like this is that I know that 1 over 1 minus y is 1 plus y squared plus, and so it continues. This is probably the first infinite series that you ever summed. So this is n is equal to 0 to infinity of y to the n. So applying that sum here, what do we have? We have 1 over 2I, 1 over x minus I, and then we have a sum from m is equal to 0 to infinity of minus 1 to the m over 2I to the m times by x minus I to the m. So indeed, we have an expansion, which is exactly of the form of the Laurent expansion. So there's the Laurent expansion over there. Here's the expansion that we have over here. And if we want the term with n is equal to minus 1 in the Laurent expansion, we want the term, so c minus 1 multiplies 1 over x minus I in the Laurent expansion. And that's the Laurent expansion. So we want the term that looks like 1 over x minus I. Well, quite clearly, looking at the equation underlined in red, we've got a 1 over 2I, 1 over x minus I. So we want the term with m is equal to 0. So from the m is equal to 0 term, what do we learn? We learn that the residue is equal to 1 over 2I, 1 over x minus I, and then the term at m is equal to 0 gives nothing there. So the residue, actually, we shouldn't keep this 1 over x minus I, it's just the coefficient. So the residue is just 1 over 2I. Okay, good. So if we go back now, what is the value of our integral now that we've got the residue? Well, let's get the pen back. There's the pen. The residue, so we've got 2 pi I times by, the residue is 1 over 2I. The 1 over 2 cancels with the 2, the I cancels with the 1 over I, and we're left with pi. So now, using the residue theorem, we got exactly the same answer as we did from our previous computation. Good. So I've shown you that the residue theorem works. We're going to apply this to our integral to do the integral over P naught. The first step is again going to be to close the contour. Once we've closed the contour, we're going to calculate the residue and then get the value for the integral exactly as we did it for the simple example.